All right, so we're doing 2-1 and 2-3a together. There is no 2-2. We're not doing that. But it still should be some pretty quick notes. Okay, so we're going to first talk about power functions. All right, so because we're getting into polynomials. So power function is any function in the form of f of x equals a times x to the nth power. Okay, where a cannot equal 0 and n cannot equal 0. So it's not a polynomial because poly means many. It's a monomial function, so it's just one term. So a power function is also a type of a monomial function. So just one term there. So we're going to draw a sketch of each. Okay, and not only the sketch is important, but the function that you actually write is as well. A constant function, which would look something like this. Well, but more horizontal. Let me cheat on it, and then I can actually make it straight. There we go. So my constant function, which has arrows, it has a constant y value, right? So this is f of x, and it's not equal to x, it's equal to a constant, so it's equal to c for constant. We know that linear is f of x equals x. So that one looks like this. Oh, well, it would help if I changed my line. Okay. Then we have a quadratic, f of x equals x squared. So we know that looks like this. We have a cubic, f of x equals x cubed. That looks like this. Okay. Quartic, f of x equals x to the fourth, like a quarter, quartic. And so maybe you don't know what that one looks like. So let's think about that. If I substitute in 0, I get 0. If I substitute in 1, 1 to the fourth is 1. If I substitute in negative 1 to the fourth is positive 1. And then when you do the 2, you're going to get positive and positive. So quartic looks, when you sketch it, it doesn't look any different than the quadratic. Because if you don't have any scale to this, it looks like a quadratic. Quintic. So f of x equals x to the fifth. So let's think about that. Substitute in 0, get 0. Substitute in 1, get 1. Substitute in negative 1, get negative 1 because it's an odd power. And then I would get the same thing for 2, and then negative 2 would be down here. So your quintic looks like this. It looks like a cubic. So when you're talking about power functions, if the degree is even, they all have the quadratic look to them. If the degree is odd, they will all have that cubic look to them. Okay? And because they have those looks, that's what happens with this symmetry. So if the function has an even power, then it is symmetric about the y-axis. Okay, so that's a little bit of a different terminology than we had talked about before. I was saying it's symmetric with respect to the y-axis. This means the same thing, but I'm using different terminology so you understand that you can be said differently and we're meaning the exact same thing. If the function has an odd power, then it is symmetric about the origin. Like even and odd functions, but it's not always just about the power to make it even and odd. It is if it's a power function. Okay, so we're tying this to end behaviors. This is kind of a review, but this is going to become even more important here. Okay, so if we have an even power, right, an even power and a positive coefficient, right? So it's a quadratic, or it has the quadratic look even if it's x to the sixth. So we know it's going to look like this when we have an even and it's a positive coefficient, which means that the end behavior is x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches infinity. If it's an even power with a negative coefficient, that's a reflection in the x-axis, so it reflects down and we'd have negative infinity, negative infinity. So notice, if we have an even power, it's either up, up, or down, down, and that's going to be what's important to us here. If we have an odd power and positive coefficient, like a cubic, this is up, this is down, right? So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. An odd power with a negative coefficient like this, that's going to be a reflection in the x-axis. So there's your reflection in the x-axis to this one. This is going to be as x approaches infinity, it's negative infinity. As x approaches negative infinity, we get infinity. Okay? So it's just the very super basic of our polynomials. So we're going to graph these. We've got 3x to the 6th. Well, this is to the 6th power, so let's think about what that means. That means that it is got the quadratic look to it, and it's a positive 3, so it'll be opening up. So knowing that, I can go ahead and fill this part in right here. So it's going to have to look, my parent function basically looks like this. Since my parent function looks like that, and I don't have any other transformations here, the only thing I would have would be the stretches and the reflections, which I would take care of there. This is going to be infinity and infinity. So then I can graph it, right? And you don't have anchor points on these necessarily, and that's okay. I mean, we can think of it that way. If your parent function is f of x equals x to the 6th, then I can start with 0, 0, 1, 1, and negative 1, 1. And then there's our other important ones, but at the same time, those would be way up off my graph. So 0, 0, vertical stretch of 3, I'm here. 1, 1, vertical stretch of 3, I'm here. Negative 1, 1, vertical stretch, I'm here. Now, if we want to think about anchor points, if I go to 2, 2 to the 6th power is 64, so it's way up there, and negative 2 would be 64 as well. So if I go to 264 and then I have a vertical stretch of 3, that's way the heck off there. So really, this is the best we can do. Super simple. All right. Domain, all real numbers, negative infinity to infinity. My range, 0 to infinity. X and Y intercept are both 0, 0. I'm increasing from 0 to infinity, decreasing from negative infinity to 0. Symmetry is about the y-axis, and no discontinuities. Right? And since these are power functions, there aren't going to be any translations up or down at all, because all I can do, and the only kind of stretch I'm going to have is the vertical. Let's look at number 2. This is negative 2x to the 5th. So my parent function would be f of x equals x to the 5th. But this has a negative coefficient, right? So my parent function, f of x equals x to the 5th, it's going to resemble a cubic, but this negative means it's going to look like this. So again, I can go ahead and do the end behavior. As x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. Okay, so that can kind of help me with some stuff too. So I have 0, 0. 0, 0 is going to have to be at 0, 0. I would have had this 1, 1 and negative 1, 1, right? So 1, 1, but I reflect in the x-axis, and I have a vertical stretch of 2. So I'm here at negative 1, reflect in the x-axis, vertical stretch. And then if I want to substitute in 2 to the 5th, that's going to be way up off my graph. So this is really all I can do. And this is what it looks like. My domain, negative infinity to infinity. Oh, that's not an infinity. Infinity. Oh, can't write. To infinity. Range, negative infinity to infinity. X and y intercepts, 0, 0, and 0, 0. Increasing, well, it doesn't increase at all. The y values are decreasing the entire time. Even through that point of inflection there, it's still decreasing. So this is none. And then this is negative infinity to infinity. Symmetry is about the origin. And there are no discontinuities, okay? So power functions, super simple, but what we're really going to focus on with this is the end behavior. So now let's look at the polynomial functions, okay? So it says a polynomial function is a function of this form. So this form looks nuts, I know, okay? But x squared plus 2x is a polynomial, right? This is written out to be like all polynomials. So I have, this is would be a coefficient, right? My leading coefficient. And then this would be my highest term, x to the nth. So maybe this is x squared. So then this would be x to the x to the n minus 1. So this would just be x. Basically, you have to go down. So this would be x to the 5th, 4th, 3rd, and where you start, wherever you start. This is the first term, or the first coefficient, then the second. And so depending on how many you have, all the way down to where you just have a constant and there is no variable on it. So if you look just at this last part, that's a quadratic. You put one in front of it, you got a cubic, another one in front of it, and it just represents all of it, okay? So the coefficients that I could list off, coefficients are the numbers in front of your variables. They are real numbers, and a sub n cannot equal 0, okay? You can have this one could equal 0, meaning I'm missing this term, but the first one isn't going to. And n is always a positive integer. Okay, so there won't be any x's in the denominators here, so no negative exponents. Our shape and continuity. Polynomials are smooth curves with no breaks, So what that means is they are continuous for all real numbers. Okay? There won't be any discontinuities because they are continuous. The degree of the polynomial, because this is important terminology that's going to be part of your assignment here. The degree is the highest exponent n is the degree. Okay? So the highest exponent, not the first, but the highest. That's why you always want to put them in order, okay, from greatest to least. And polynomials are classified by degree. Okay. So let's look at these examples. It says identify the degree and classify each polynomial function. Okay, so the degree of this one, the highest exponent. Well, I don't have any exponents. I don't even have any variables. So what I could say about this one, I could say that this is f of x equals 2 times x to the 0 power. Okay? And anything to the 0 power is 1. So that means my degree here is 0. My degree on this one, the highest exponent, is 1. So when you have more than these, you have to make sure they're in order. Don't always just take the first one. 2 is the highest, so this degree is 2. 3, 2, 1, 3 is my highest. And then these are all in order, so this is 4 and this is 5. because those are the degrees, and then we classify them. This is constant because your degree is 0. This is linear, that's old news. Okay. This one is a quadratic, old news. Cubic, old news. Quartic, you've probably talked about at some point. And quintic. Okay, but we can also refer to it as a 4th degree polynomial, a 3rd degree polynomial, those sorts of things. Okay, now this next little part probably looks identical, well, not probably, it looks identical to the first set we just did, but I had the blanks in here for end behavior, but we're not writing the same thing. Because yes, we need to be able to do it the way we've been doing it, as x approaches infinity, f of x approaches, blah, blah, blah. But when we start sketching, because we're going to start sketching these, not graphing, but sketching polynomials, and when we get there, I'll talk to you about what the difference is. We are looking at, again, the end behavior. Don't care about what's going on in the middle here. So here's what we know. We know that if it is an even power and it's positive coefficient, the end behavior resembles a quadratic. So when you have to write end behavior when we are sketching, and I'll show you when we get there how it's going to look different, I don't want to write out those words. That's not what's going to help me. What's going to help me is to know that the end is up, up. That's what I need. The middle can be a hot mess of stuff, and we'll look at that in just a second. I'm talking end behavior. End behavior. Because these are not just going to be power functions. If it's an even and it's a negative coefficient, it's going to open down. And so my end behavior would be down, down. No matter what's going on in the middle, it's down, down. Odd and positive coefficient would resemble the cubic, so it's going to be down, up like this. Odd and negative, it's like a reflected cubic. So it would be up, down. And these little arrows are literally what we're going to draw. So here's the kinds of things we're going to be looking at. If I give you some crazy graph that you don't know the equation of and you've never necessarily seen before, it could look something like this. You should be able to tell me if it's an even or odd polynomial, if the leading coefficient is even or odd, and if the leading coefficient is positive or negative, okay? So since this is up, up, this is going to be, it looks like this. That means it's an even power and a positive coefficient. If I give you a graph that looks like this, okay, then the ends are opposite, which means it's an odd power. And since we know that a cubic goes like this, and this is the reflection of it, this is up, down instead of down, up, this would be an odd power with a negative leading coefficient. Right? Those are some of the kinds of things we're going to be looking at here. So let's look at these examples. It says using the leading term, okay? Not always the first one you see, but the highest one. And these may be all set up that way. But you got to be careful because maybe I should have mixed some of these up. Just because I look at this and I see the 4th first, that doesn't necessarily mean it's a 4th degree polynomial. I got to make sure that's really the highest one. So when I look at this, the 4th is the highest one, so that means that this is a quartic. It's a quartic. My leading coefficient is to the power of 4, and it's negative. So it's an even and it's negative, which means my end behavior is down, down. This, I look at my exponents. My highest one is a 5, so that is a quintic. So it's odd, which means the ends are opposite, and this is negative, which means it's up, down. Okay? If it helps you to have, like, just, draw yourself a quadratic and a cubic to look at, so you know that that would be even positive, odd positive, and then you can think about what the negative ones are. So then we have, this one is squared, so this is quadratic. and then decide if it would be up, up, down, 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 up, down, what it would be. Well, it's a quadratic, so, and it's positive, so it would have to be up, up. Okay. So this is the highest degree, or the highest power, makes this a 7th degree polynomial. And that wasn't on a little chart of names, but think about what 7 means in, or you use your prefixes from chemistry or from a foreign language or whatever. There's actually 2 different ones you could use for 7. You can use sept and hept, but this is called a heptic. Okay, so it's a heptic. It is odd, and the leading coefficient is positive, so it's going to be down, up. All right, we're going to be using that a lot. So now we're going to do the opposite, kind of like we did on the front page here. We're going to look at these. It says describe both the power and the coefficient. The power and the coefficient of the leading term of the polynomial. Okay, so these, the ends are opposite, so this is an odd power. And then think about whether it would be a positive or a negative coefficient. Remember, your cubic looks like this. That's the opposite, so this would be a negative coefficient. Right? Then I look at 8. The ends are the same, so that makes this an even power. And they're up, up, so this is a positive coefficient. Right? Okay, so turning points. We've looked at these a little bit already with our maximums and our minimums and whatnot. But it says the point or points at which a polynomial function switches direction. That's what our maximums and minimums are. If the turning point is higher than any nearby point, it's called a, and notice it says nearby point, it's called a relative maximum. Right? If the turning point is lower than any nearby point, it's called a relative minimum. We could still talk about absolute maximums and minimums. This one doesn't have, this particular graph doesn't have one. But if I made one that looked like, you know, like this, then yeah, I could still have an absolute minimum. But remember, it's also called a relative minimum. Okay. And then maximum and minimum values together are called extrema. That is plural for extreme. And then your turning points define where the function is increasing or decreasing, where it's changing that. Remember, we cannot find these things algebraically right now because that requires calculus. But we're still going to, that's why we're going to be sketching things and not graphing them because we can't find them exactly. This says using a calculator. We absolutely are not doing that. We could find the maximum and the minimum by punching buttons on the calculator, but that teaches you absolutely nothing. So totally not doing this. Not necessary. You using a calculator on this is not going to help you any, because the whole idea is that you have a concept of what's happening, not that you can push buttons on a calculator and it can spit stuff out at you. All right? So that's that for today.